Hello, my name is Matthew Castronovo, and this is my Physics Lab 5 Magnetic Molasses. As an introduction, the goal of the lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnetic tube and interaction between the magnet and the tube computationally, and compare the real and computational results. Some key concepts to keep in mind as we move forward with this lab: Faraday's law, which is obviously the way that a change in flux over time affects an induced EMF and induced current. Magnetic fields and forces, obviously, we've been working with those most of the semester, and induced EMF and current due to Faraday's law, and Lenz's law, which is probably the most important part of this entire lab. It's the negative in Faraday's law. Well, actually, I'll just go to the next slide real quick. So in Faraday's law, you can see that there should be a negative for the if this were not the absolute value of the change in flux over change in time. And essentially, what it means is that the induced current will move in such a way that the magnetic field opposes the change in magnetic field over time. Essentially, it's saying that if a if something's moving, changing in time, nature wants to stop that as much as possible. And so, for the purposes of our lab, that changes in velocity. And so, the way that nature is going to try to change that is the new magnetic force is going to oppose that of the force of gravity, not totally canceling it, but somewhat making up for it. And just to go back, the results, so that preview of the results, that the average experimental fall time was 1.276 seconds in the tube. So the experimental setup and results, we dropped a magnetic dipole through a non-ferrous cylinder. The magnet took much longer than usual to fall through compared to if it were not within a magnetic cylinder. And here's some dimensions of the cylinder. Its length, width, inner radius, and outer radius, you can see, and its resistivity, and then the magnetic mass and the magnetic dipole we also have. And so here's a video of the experiment. So we ran that trial 5 times and came up to that average of 1.267 or 76. So here are just a few bits of my computational model, parts that I actually worked on. It's first with the initial conditions up top right, and then step one, we edited the magnet to give the correct mass and magnetic dipole moment. And then the bottom two functions. The first was to calculate and return the magnetic field of the bar magnet, and the second was to calculate the change in flux over change in time of the magnet, which we did using obviously what we know about the definition of Faraday's law. And so you can see all of that right here. The results are that the computational model actually predicted that the magnet was going to move through in 0.302 seconds. And that is pretty far off from our experimental value. So that necessitates a discussion of the possible sources of error, which could include human error in the experimental procedure, namely when we were taking the video of the falling magnet, the timing could have been off, neglecting air resistance. That was something we did in our calculation. And so there are definitely reasons why we could have seen it, as well as possible errors in the code. And so here's a discussion on, first of all, what if the resistivity of the conductor were reduced as close as possible to zero? Well, that would make it so that we know that EMF is equal to IR, and so we see that the current becomes much greater the closer that the resistivity is to zero. And so essentially what we're going to see is that it has less and less of an effect the less resistive the magnet or the cylinder is. And what if the holes or slots were cut into the tube? That would mean that no current can pass through the tube. Therefore, there would be none of this effect. There would be no magnetic braking because you need current in order to see this effect.